In this lesson, we will complete lesson 4.4, determining restrictions on composite functions. We've completed 4 examples in this section. So today's lesson will review questions on determining restriction and composite functions from your textbook. So we look at 2 questions from Check Your Understanding and 4 questions. 1, 2, 3, 4. There are parts of these 4 on exercises on pages 314 to 319. In this lesson, our goals are to sketch graphs of composite functions, determine equations of composite functions, and identify restrictions. Just to recap, a composite function is the result of applying 2 functions in succession, and we can sketch a graph of a composite function. And also for some composite functions, there are restrictions in the domain. And we went through a process of identifying the domain of a composite function. We'll go through a few more examples on how to identify restrictions on composite function. So let's look at question. First example is on your textbook 3. Now, just to recap, this example asks you to find the domain of a composite function. Whenever you find the domain of when you're asked to find the domain of a composite function, we want to follow a simple step-by-step process. So, for example, if we have f g of x, we find the inside function first, the domain, then evaluate, in other words, find the explicit equation for the composite function, then find the domain of a new composite function. And the composite function domain must also include the function of the inside function, the domain, of the inside function. Question 1, example 1. You're given functions f of x and g of x. And you are to determine an explicit equation for each composite function. There are 2 composite functions. So let's look at the first one, g f of x. We have f of x given as the root of x, g of x equal x squared minus 4. Step 1, find the domain of the inside composite function. So the domain of the root of x is where x is greater than or equal to 0. Because we know this graph will be coordinates from 0. So y is equal to the root of x. This is a quadratic. We can write a domain is x is a set of real numbers. Now, our composite function, that's step 1. We go back here. Step 1, we find the domain of the inside function. Step 2, evaluate and simplify the composite function. So step 1. So step 2, we have g of x is x squared minus 4. We will replace x with the root of x, because that's what f of x is. So g f of x is equal to the square root of x to the power 2. I'm just replacing the x by root of x minus 4. Simplify. The x minus 4. Now, if we look at this, so this is a straight line. The domain here would be x, a set of real numbers. But f of x, the domain is x is greater than or equal to 0. So recall in our first statement, or initial statement, we have to take into consideration the first functions. In this case, inside function is domain, which is x is greater than 0. So this must take into consideration this domain. So although x minus 4 is a straight line, all real numbers, you must include the first function f of x. So the domain, g f of x equals x minus 4 is x is greater than or equal to 0. Let's go on to b, f g of x. I'll rewrite my f of x is equal to the square root of x. We know the domain x is greater than or equal to 0. G of x, domain x, so the real numbers. So step 1, we identify the domain. So we identify the domain of the inside function, which is x set of real numbers. Now we find the explicit equation of the composite function. So the explicit equation you have g of x is equal to x squared minus 4. So we'll substitute x squared minus 4 into greater value x here. So we have f of x so replace x with x squared minus 4. So f of g of x squared minus 4. Now look at the domain of g of x, set of real numbers. But look at the composite function. There's severe restrictions here. So now this cannot be negative. So x squared minus 4 cannot be negative because you cannot have a negative square root. So since x squared minus 4 must be greater than or equal to 0, we find the restrictions. So we have, in this case, we have x squared minus 4 must be greater than or equal to 0. So we have x squared is greater than or equal to 4. We have x squared is greater than or equal to 2. We have or x is less than or equal to -2. So we have our number line to prove that. Here we have, if you go back to this equation, your result is x, -2 and 2. And if we were to use test value, if you test -3, or on +3, or if you try 0, let's try 0 here, test using 0. Into an equation here, we have x squared minus 4 must be greater or equal to 0. So you have 0 squared minus 4 is not. So we know it's not restricted. So if you try 3, x equal 3, sorry, -3. So we have x squared minus 4 is greater or equal to 0, -3 to the power 2, 9 minus 4. So we have 5 is greater than 0. So we know it's valid here. And the same thing we would try for x equals 3, and you'll find it's also valid. So that's what our restrictions or domain x is less than or equal to -2, or x is greater than or equal to 2. So whenever you're asked to find the domain of a composite function, find the domain of the inside function and find the domain of the composite function. And if there's any restriction of the inside function, that must be taken into consideration into your composite function. In this case, the composite function, the restriction must be greater than or equal to 0. And you can use a number line to evaluate the restriction or solve for your equation. Question 4, for each function, determine possible functions of f and g so that y equals f of g at x. Basically, you're working backwards in these questions. And there are a few possibly answers, but I'll look at one possible answer. We have y equal x minus 2 to the power 3. So y is equal to fg of x. So we place fg at x is equal to x minus 2 cubed. Because they give us that y is equal to f of g at x. Now, g of x is our inside function. So if we let this be g of x, will be x to the power 3. So replace x minus 2 with x. And that will give us f of x. So f of x is equal to the x to the power 3. G of x is equal to x minus 2. We can show that is correct by, or is valid by the reverse. So we have f g of x or f of x is x cubed, and replace that with x minus 3. So we do it separately. We have f of x equals x cubed, and we have g of x is equal to x minus 2. So replace this x with x minus 2. So f is exactly what we have. So f of x is equal to x cubed, and g of x is x minus 2. Let's go to the next one. B. Y is equal to the square root of x3 plus x. So f g at x equals 3 plus x. So let f of x equal root of x, g of x, 3 plus x. And to show that's true, so we have f of x equals root of x. Replace x with 3 plus x. F of g at x we look at a couple of other equations, questions. Let's look at exercise 3a and b. For each function, determine possible functions of f and g so that y equal f g of x. Similar to what we just did. So we'll look at the first one, a. So we have f so replace x plus 4 with x. F of x now becomes x squared. G of x is x plus 4. B f g replace x plus 5 with x. Then f of x is root of x, and g of x is equal to x plus 5. Here are two questions, and you're asked to sketch a graph of each composite function, then states its domain and range. The easiest way to do any of these is to create a table of values for the functions. So Step 1, make a table. For both functions. So let's construct a table of values here. So the first will have x. And generally we choose integers from maybe -4, -3 to +4 or 3. So in this case, I'll choose -4. It's my x value. -3, -2, -1, 0. One, 2. We can go to 3, but we'll stop for 4. Then we have f of x. Now, f of x we said is x plus 3. Next, we ask for a. We'll have f of x, which now will change to, we have f of x plus 3. We have g of x, and g of x is x squared plus 1. And finally, we have f of g of x. That's what we asked to find. So f of g and x, which will be g of x plus 3. So we complete a table of values here. So when x is -4, f of x is -4 plus 3, -1. F of f at x, so we have -1 plus 3, so -1 plus 3 gives me 2. We go into g of x, so we take our x -4 plus 1 gives me 17. And f g of x, so we have a g of x, and we have f of x, so g of x is 17 plus 3, 20. And if you get through the entire process, it would be 0 here, 3, 10, 13, 1, 4, 2. So we see -1 plus 2. So you have 2 plus 3 is 5. We have -1 plus -1 to the power 2. So it'll give me 4 plus 1. So we have what, negative 1 square plus 1 gives me 2. So 2 plus 3, 5. Then you have 0 plus 3 is 3. 3 plus 3 is 6. 0 squared plus 1 gives me 1. We have 1 plus 3, 4. So we have 4 plus 3, 7. We have 1 squared plus 1, 2. 2 plus 3, 5. 2 plus 3, 5. 5 plus 3, 8. 2 squared plus 1, 5. 5 plus 3, 8. If you continue the process, we have 3 plus 3, 6. Notice there's a pattern here. Then we have 6 plus 3 be 9. This would be 3 squared plus 1 gives me 10. 10 plus 3, 13. 4 plus 3, 7. 7 plus 3, 10. 4 squared plus 1 is 17. And we have 17 plus 3, 20. So here we have our values. And we will construct a graph. Y-axis. And this is my x-axis. Now the next one is quadratic. So let's look at the first one. So we have x, f of x. So this is my x value. So I'm going to use these two two columns values. So we label as what, 2, 1, 2, 3, negative 1, negative 2, negative 3, 5, 1, 2, 3, 5, 6, 8. So x negative 4, y 2, negative 4, 2, 0, 3, oh, I did it right. Oh, sorry, incorrect here. 0, x equal 3. It should be 6. Oh, incorrect here. Okay, I'll do sequence here. Sorry, 6 wouldn't make any sense here. So that's my line. Oh, next graph, f g of x. So it will be negative 4, 20. So we have negative 1, 1, 2, 3, 4, negative 4. Negative 420 is off my scale here, but I'll use this as 1, 2, 3, 4, 5, 6, 7, 8. So negative 420, negative 3, 13, no, negative 2, 8. So negative 2 and 8 will be here. we have negative 1 and 5. 1, 2, 3, 4, 5. Zero, 4. Have 1, 5. 2, 8. The domain for the first f of x is y equals f of f at x. Domain x is real, and the range y is set of real numbers. Y f of g at x, domain x. Now the range y is greater than or equal to 4. Question 6. For each pair of functions below, determine the explicit equation. For indicated composite functions, state the domain of the composite function. So remember our guidelines. Step 1, we find, so this is where we have to find g f of x. G of f at x. So we have a, so f of x, root of x plus 1, and g of x, x squared minus x minus 6. Step 1 asks us to write the explicit equations. And step 2 asks you to find the domain. Well, let's find the domain first. It's a little bit more straightforward. So the domain, notice, is the square root of x plus 1. Since we cannot have a negative square root, then x has to be greater than or equal to negative 1. Because less than negative 1, then it becomes undefined. So the domain here would be x is greater than or equal to negative 1. This is a quadratic, so the domain is x set of real numbers. So our inside function is f of x. So our composite function must take into consideration the domain. X must be greater or equal to negative 1. Let's find the composite or explicit equation. And then we'll find the domain of the composite function. So g of x equal to x squared minus x minus 6. So replace x with square root of x plus 1. of f at x. So I'm replacing x with x squared of x plus 1. Minus the square root of x plus 1 minus 6. So now this is my explicit equation. And I could simplify that. So I could put here. Of composite function. So simplifying, this becomes x plus 1 minus x plus 1 minus 6. Combining like terms, we have x, negative 6 and 1 gives me negative 5. Now, the domain of f of x is greater than or equal to negative 1. So domain, and if you look at the composite function, there's no restriction. The only restriction applies to the radical. Domain g of f at x x is greater than or equal to negative 1. Because the domain of any real numbers has to be greater than or equal to any values in the square root. Question 9. Given the function y equals x over x minus square root of x minus 3, determine the possible fractions f and g so that y equals f of x over g of x, and f and g and h so that y is equal to f of x over g of h at x. So basically, you're being asked to find sample solutions with f of x, g of x, what f of x could be and what g of x could be. In this case, it's quite straightforward. They ask you f of x, we can make that as equal to x, and g of x equals the root of x minus 3. So y equals f of x, g of x. And there are other possible solutions. We f of x is equal to x, and g of x, root of x minus 3. B, and we have area of x so now we have g of h at x. So replace x minus 3 with x. So we replace x minus 3 with x, and we let h of x be x minus 3. So therefore, g of x will be the root of x. So if h of x be x minus 3, g of x will be the root of x. And f of x will be equal to x. So it should look, if we were to replace all of these, we have y, f of x is x, g h of x. So we have replace the x with x minus 2, will give me x minus 3. Sorry, x minus 3. We'll look at question 10. Given the function f of x equal the root of x, g of x equals x squared minus x plus 6, and k of x is equal to 2 over x, write an explicit equation for each combinations. So we have two combinations. We look at the first one. H of x equals f of g at x plus k of x. And we're given f of x k of x 2 over x. So let's look at the first one here. So for f of g at x, so we look at f of x, which is f of x replace x with x squared minus x plus 6, because this is g of x. X squared minus x plus 6. Now k of x is 2 over x. So we have h of x now. F of x. I'll rewrite it here so to make it a little bit more clear. F of g of x is the root of x squared minus x plus 6. I'll replace f of g at x squared minus x plus 6, and k of x is 2 over x. In this case, x cannot be 0, so we know x cannot be equal to 0. Now, if they were to ask to find the domain, it will take into consideration the domain is x real numbers, x is not equal to 0, and x is greater than or equal to 0. So it will take into consideration all three. So your domain would be all the values greater than or that greater than would be the domain in this case here. To work it out, be considering all of these, but also this has to be greater than 0. So for P, h of x, g f of x minus f of g at x so we'll look at g f of x first. G of x is x squared minus x plus 6. Replace x with what f of x is. F of x is the root of x. So g f of x equals we have the this becomes root of x squared, just replacing minus root of x plus 6. So that's g of f at x. Now f of g at x. So f of x is equal to root of x. Replace x. No, replace x with x squared minus x plus 6 f so now we'll replace f of g at x with root of x squared minus x plus 6. And this goes in there, it goes up there. So let's finalize this. So g of f at x minus so g of f at x gives me, will be squared. This can be x squared minus root of x plus 6 minus the root x squared minus x plus 6. and where x must be greater or equal to 0.